Problem 6 asks what volume of chlorine gas measured at STP is necessary for the complete reaction of 4.81 grams of sodium metal. Now we know that at STP, 1 mole of any gas, of any ideal gas at STP, fills 22.4 liters. So we can just use this value instead of having to use the ideal gas law. And that is because our gas is being measured at standard temperature and pressure. So what we need to do here is just some stoichiometry. We'll start with 4.81 grams of sodium. And we'll first convert our grams to moles. 1 mole of sodium is approximately 23 grams. Then we will go from moles of sodium to moles of our new substance, which is chlorine gas, or chlorine, Cl2. And then finally, we will go from moles of chlorine gas to liters of chlorine gas, using our 1 mole equals 22.4 liters at STP. So to get our mole-to-mole ratio, we do need to balance our chemical equation. Right away, I see 2 chlorines on the reactant side, so I put a 2 in front of NaCl. Then I also need to put a 2 in front of sodium to balance out the sodium. And of course, if you want, you can fill in a 1 in front of Cl2. That gives us our mole-to-mole ratio. For every 2 moles of sodium, we need 1 mole of Cl2. So now all that's left is to multiply and divide. 4.81 divided by 23 divided by 2 times 22.4 gives me 2.34226. But of course I do need to round that to just 3 significant figures, just like I had in my problem. And so let's take a look at that. 1, 2, 3 digits I get to keep. And so I will round my final answer to 2.34 liters. And I do need to make sure I put a substance on an answer. It's asking for amount of chlorine gas, so this is liters of Cl2. And then that is our full finalized answer right there. Number 7 asks what volume of oxygen gas at 25 degrees Celsius and 1.04 atm is needed for the complete combustion of 5.53 grams of propane. So in this problem, our gas reaction is not occurring at STP. And so we are going to need to use both stoichiometry and the ideal gas law to solve this problem. Let's go ahead and start out by balancing our reaction. We'll need to put a 3 to balance the carbon, and then a 4 to balance the hydrogen. Then if we add up our oxygens, we have 2 times 3, 6 oxygens, plus 4 oxygens for a total of 10. So we can put a 5 in front of O2 to balance out the oxygen. And then we'll just fill in a 1 in front of C3H8. So now that we've balanced, we want to start with our given value in the problem, 5.53 grams of propane. 5.53 grams of propane, so C3H8. We're going to start the same way we did the previous problem by going from grams to moles of C3H8. 1 mole of C3H8 if you add up its molar mass, so about 12 times 3 plus 8, you get about 44 grams per mole. Then we can go from moles of C3H8 to moles of our desired substance, so oxygen gas, moles of O2. And this is where we have to stop. We cannot use 22.4 here because our gas is not at STP. So once we solve for our moles of O2, then we'll have to use the ideal gas law, PV equals nRT, to solve for our volume of oxygen. Since we are not at STP, we're at 25 degrees Celsius and 1.04 atm. So let's finish this setup. We have 5 moles of oxygen for every 1 mole of C3H8. So now we can solve this out. 5.53 divided by 44 times 5 gives me 0.6284 moles of O2. And so that number of moles is going to be equal to our N in PV equals nRT. So let's go ahead and write out the ideal gas law. Now we need to isolate V, so I'm going to divide by P on both sides. So I get V equals nRT divided by pressure. Now, our pressure value is given in the problem as 1.04 atms, and that's already in the correct unit of atms. I know our gas constant that we're given has units of atms as the units of pressure. The problem is the 25 degrees Celsius. We do need that to be in Kelvin, because any gas law we need temperature to be in Kelvin. So we'll go ahead and take that 25 degrees Celsius and add 273 to convert it into the Kelvin scale. So that gives us 298 Kelvin. So now we have everything in the correct units, so we can go ahead and substitute in. We'll take our number of moles that we solved for previously, 0.6284, times our value of R, which is on your formula sheet. It's 0.08206. It's just a constant, times our T value in Kelvin, which is 298. And then we'll divide by the pressure, which is given in the problem as 1.04 atm. So all that's left is to solve this. When I multiply and divide this out, I get 14.7760. Of course, I will need to round to correct sig figs. And given in my problem, all of the values have either 2 or 3 sig figs. The smallest number of sig figs is actually that 25 degrees Celsius. And so we'll go ahead and round our answer to 2 sig figs here as well. So right here, we'll go ahead and round to 15, because the 14 will round up. 15, and then this is a volume, and our units in our gas constant are liters, and so this is going to come out in liters as well. So 15 liters of O2 is our final answer here. Number 8, what volume of chlorine gas measured at STP is needed to produce 10 grams of KMnO4? So let's start by balancing our equation. We know we're just going to need to use stoichiometry. Since this is at STP, we know that 1 mole of any gas at STP is equal to the same volume of 22.4 liters. So we can kind of start there. We'll balance our equation, do some stoichiometry to get us our final answer. And so right away I see that Cl is out of balance. There's 2 on the reactant side, so I'm going to put a 2 in front of KCl on the product side. Doing that actually makes an odd number of potassiums, which is not going to balance out with the 2 potassiums on the reactant side. So I'm going to even that out by putting a 2 in front of KMnO4. Now I have 4 potassiums on my product side, so I can go ahead and put a 2 in front of K2MnO4 on the reactant side. And then once I do that, everything's in balance, and I'll just fill in my 1 in front of Cl2. So now let's start with our given value of 10 grams, 10.0 grams of KMnO4. And we'll start by converting our grams to moles. And the molar mass of K2 or of KMnO4 is about 158 grams per mole. You can add that up and calculate it out yourself. 158 grams per mole. Then we'll take our moles of KMnO4. It's a lot to say. To our moles of our new substance, Cl2. And since this is at STP, we know that 1 mole of any gas at STP fills 22.4 liters. If we don't need to use the ideal gas law, we can just use that conversion factor. All we need to fill in is our mole ratio. For every 1 mole of Cl2 that is consumed, we get out 2 moles of KMnO4. So we just need to multiply and divide. 10 divided by 158 divided by 2 times 22.4. And when I solve this, I get 0.70886. And we are going to need to round to 3 significant figures. Remember, the leading 0 is not significant, so we just still get to count 1, 2, 3. And then this 8 is going to cause the other 8 to round up to a 9. So our final answer should be 0.709. And this is liters of Cl2. You also could write this in scientific notation and write 7.09 times 10 to the negative first liters of Cl2. Either way would be acceptable. And so either of these answers is perfectly all right, either in scientific notation or in standard notation.